I think. Yeah, that's what it is. Okay, cool. So recording started. So why don't we get a start on this? So obviously if you have like an iPad, this is really nice to follow because you can just follow what I'm doing. But if you don't, I would recommend printing. You can print these out, and then you can just write as we go. Either or, you could just do an exercise book or something like that. So it's not too big of a deal. But anyway, so let's go from the start. So we're learning about integration techniques. So obviously in methods we've learnt, how to do integrals with like single functions, right? Like, cos x by itself. But what happens if they're like, combined, in the forms of like whether like a product or, they're divisible or something crazy like this. So the first technique we're going to talk about is U substitution. Here's the formula to do it. Um, you don't really need to know this. I think doing it is a lot better and a lot easier to understand. So why don't we just try exercise 1.01 first? So, non-linear substitutions, what I mean by that is linear substitutions you've actually done in methods, right? So when in methods, you know how to integrate something like 3x plus 7 to the power, I don't know, by 7 dot dx, right? Your reverse chain ruling, right? That's the same concept. That's a linear substitution. You're basically doing U sub, but you're doing it reverse, right? But more in specialists, we're focusing on non-linear. So it's something that's kind of harder to do. So for example, in this first question, right? Um, how do we do this? Well, we can see that inside this brackets here, if we decompose it and derive it, we get something of the same power, right? So for example, if we let u equals 1 minus x squared, right? Du is going to be negative 2x. We can substitute that in, right? With u sub. Um, can substitute that in. And so our integrand becomes x, square root of u dot dx over negative 2x, right? So what I've rearranged here. So then the x's cross out. So you get, we can bring the negative a half, right? Take the constant out. And, oh, sorry, this should be du, right? So now we're integrating in respect with u. So in this integral, we can just, it's the same as a half, right? So this would be, we take the, raise it by 1, and then we divide by the new power, so times by 2 on 3, right? So you'll get, and then plus c. So then you'll get negative 1 on 3 u to the 3 on 2 plus c. And then you just resubstitute what u is, right? And at the start, we defined as 1 minus x squared. So that's what we're just going to do. So we're just going to do 1 over 3, 1 minus x squared to the power on 3 on 2 plus c. All right, does that make sense? Um, I'll also assume if there's like nothing, like no hands up or anything, it's pretty chill. So I'll just move on. Please do speak up if there is an issue. Um, that would be good to know. All right, cool. So that should be it. The first one. All right, cool. Second one. So we've got a integral here with trig functions, right? So for this one, does anyone have a suggestion what we should do our substitution as? So what we should let u as? You can unmute the mic and just scream out. Anyone want to have a go? You can also type it in chat if you'd like to. It also works out. But if no one wants to have a go, I think we should let the denominator be u, right? Because we can recognize that if we derive tan x our the derivative of tan x is sec squared x, right? So it's something similar to our numerator here. So we're just going to let u equals 10 plus 2 tan x, right? Du, right? Derivative is going to be 2 sec squared x dot dx. Okay. Now we can just substitute it in the integrand. So therefore, our integral becomes sec squared x over u. All right. And we would do times by or dot du over 2 sec squared x. All right. The sec squareds cancel out. And then you're just left with 1 over 2, 1 over u dot du. And this is just a log, right? So we get 1 over 2 ln ln 10 plus 2x plus c. Okay? So that's pretty chill. Okay, any questions with this question? Should be stock standard stuff that you've learned already. Nothing? All right, cool. Let's move on to the next one. So the next type of integrals that you can have is powers of trig. So they're usually in the form of what I've shown here, right? And just a little trick to know. So how do we solve these? Well, if one of them is odd, right, we use a u sub, right? And but rewriting it using the this identity, right? So we use this identity, we rewrite it, and then use a u sub. But if it has an even, right, then we use a double angle formula. All right. So we're just gonna go through some examples of those. So for the first one, we get just cos to the power 4 by itself. So because it's all even, right? Both m and n are even. Well, in this case, it's just, just the cos, right? Because they're both even, we're going to use some double angle formula. So in your specialist, what's it called, formula sheet, you should see under the double angle formula, it should be like, I'm going to rewrite it, but it should look something like this. 1 plus cos 2 theta or cos 2a, right? I think originally it's given by cos 2 theta and equals whatever. So we're just going to do that, right? And we're just going to substitute it in. So now that we know this, we know that, cos 4 theta would be double that, right? So cos 4 theta is going to be, what's it called? We take the half, 1 plus cos 2 theta, and we square everything, right? So, yep. And cool. So if we expand this like a quadratic, we should get 1 over 4, 1 plus 2 cos 2 theta plus cos 2 squared theta, right? So after we've done this, yeah, we can see that, okay, this we want to decompose again using double angle formula, right? So we can see that cos 2 squared theta is equal to 1 over 2 plus cos 4 theta, right? We're just basically doubling, oh, sorry, multiple, raising a power by 2. And so we can substitute this in for that. So in the end, therefore, we know that cos 4 theta is equal to 1 over 4, 1 over 4, 3 on 2. Um, oh, sorry, 1 over 4. 1 plus 2 cos 2 theta plus 1 half 1 plus cos 4 theta, right? We're just substituting this thing into here, right? Just rewriting it. We can expand this, right? So if we expand this, we will get 3 on 8 plus 1 over 2 cos 2 theta plus 1 over 8 cos 4 theta. Okay. So now that we've done all of this trig identity stuff, we can just integrate, right? So we can rewrite the integral. So cos to the power of 4 theta dot theta equals the integral of 3 on 8 plus 1 on 2 cos 2 theta plus 1 on 8 cos 4 theta dot d theta. And we can integrate this, right? Like any method student can do this, so you definitely can, right? And so our integral becomes 3 on 8 theta plus 1 on 4 sine sine 2 theta, right? Plus 1 on 32 sine 4 theta, and then plus c. Okay, does that make sense with this one? If anyone has any objections, please let me know now. No, it's all good. All right, let's continue then. So let's continue. So next one, we've got a definite integral. Sine 5x cos 6x. So from our rule before, when one m or n is odd, we use this, right? So let's try and apply that here. So generally we use the odd term, which would be the sine in this case, but you can use either. The odd is just lower, so it's actually very convenient. So we can split our integral. We can rewrite it as pi on 2 sine, 4x, right? Cos 6x sine x dot dx, right? We're just taking a sign out. And so we can see that sine 4x is equal to 1 minus cos 2x squared, right? Using our trig identity in our formula sheet, right? So after we use this trig identity, we can sub it in, right? So therefore our integral becomes 0 pi on 2, 0 pi on 2, 1 minus cos 2x squared cos 6x sine x dot dx. Okay, cool. Now that we've only got a single sign left and just the rest of them written in causes, we can use u sub, right? So we can just do that. So let's use u sub. So let u equals cos x. du is going to be negative sine x, right? Dot dx. So therefore our integral is rewritten as 1 minus u squared u to the power 6 sine x dot dx over negative sine x. All right, sine x's just cancel out very nicely. We can drag the negative to the front, right? So pi on 2. And then we can also expand what's inside of the brackets. So let's do that. So that would be u to the power, how about I expand this? Minus 2u squared plus u cubed, right? U to the power 6. And, oh, sorry, I keep writing in dx. It should be du, right? So du here, we can expand it one more time, and we can just treat this integral like a polynomial, right? So u to the 6, 2u to the 8, plus u to the 10. dot du. Cool. Let's do the integral. So we get u to the 7 on 7 minus u to the 9 on 2 on 9 plus u to the 11 over 11. 0 pi on 2. Oh, sorry. I shouldn't be putting that there. These terminals aren't right. Ignore me for now. We're going to put the terminals after we resubstitute the u back in. So we're going to resubstitute our u now. So it was cos x's. So we're going to rewrite it as cos x's. So cos 7x over 7 minus 2 cos 9x over 9 plus cos 11x over 11. So now that we've done this, we can just, okay, our terminals are x equals 0 and x equals pi on 2, right? From the start of the question. Sub it in, right? So, what's cos pi on 2, guys? Do we know what cos pi on 2 is?
1.
1. Yes, yes. Oh, no.
Wait, hang on.
Again. Well, what does cos graph look like?
Oh, pi on 2. I was thinking of 2 pi.
Yes.
0, isn't it?
0.
Yeah.
Okay, cool. And then what's cos of zeros?
Cos of 0 is 1.
Yes. Okay, so basically all of the pi on 2 terms cancel out, right? So there's no point of writing them. Yeah. So we got 0 minus, okay? And then don't forget the minus at the start here. So go minus again. And then we get 1 over 7 minus 1 over 2 over 9 plus 1 over 11, right? Cool. So this would be positive, whatever this gets you, right? So positive 1 over 7, 1 over 9 plus 1 over 11. Oops. Um, and on this answer sheet, I got 8 over 693. Okay, cool. Any questions to this style of integrals? It's a bit long, but you just got to go through it. There's nothing too bad. We'll continue. No, yes, no, yep. Okay, let's just continue then. All right, now we have two odds, so we'll do the same thing, all right? It doesn't really matter. So this time I'm gonna take I'm gonna rewrite the causes. So we'll split the cos, right? So our integral becomes sine 5x cos 6x cos x dot dx. Okay, so we know that cos squared x equals 1 minus sine squared x. Cos 6x is the same as writing cos 2x to the power of 3, right? Which is the same as 1 minus sine 2 to the power of 3. Yeah. Dot dx. So we're just going to substitute all of that in. So therefore our integral becomes sine 5x and this would be 1 minus sine 2x to the power of 3 cos x dot dx. Okay, now we're going to do our u sub. So let u equals sine x. du is cos x dot dx. Okay. Then we can just replace everything by u. So therefore our integral becomes u to the power of 5. God. 1 minus u to the u squared to 3 cos x dot du over cos x. And you can see that the cos x is just cancelled, right? So that's nice. All right, cool. Then we just expand. So we want to know what this expansion is. So let's just do that. So 1 minus u squared to the power of 3. It's going to be this u squared plus 3u4 plus minus u6. All right, so it's just a cubic. Oh, sort of. Okay, cool. And then our integral becomes u to the power of 5 minus 3u to the power of 7 plus 3u to the power of 9 minus u to the power of 11 dot du. Okay? And then we can just integrate this pretty easily. U to the 6 over 6 minus 3u to the 8 over 8, 3u to the 10 over 10, u to the 11 over 11, 12, sorry, over 12 plus c. And then we can resubstitute our causes. So our causes, sorry, our sines. So it'd be sine 6 over 3 sine 8 plus 3 sine 10 plus, minus sine 12 over 12 plus c. Okay, cool. Any questions? No, yes. Anything? Okay. I guess we continue then, if no one's saying anything. All right, cool. So we go to just a few things about inverse trig because you do have to integrate things back into inverse trigs, right? So here are some inverse trig graphs. I don't think you're expected to know them, but here's some characteristics that I have here, right? What we can recognize is that the domain of our inverse trig function, right? Like y equals arc sine x. Oh, sorry, arc sine is the same as sine inverse, right? Sine inverse 1, right? So if I say arc sine, it's the same as sine inverse 1. We can see that the domains of each one is the same as the ranges of our normal trig function, right? So in this case, our sine y equals arc sine x, right? The domain here is the same as y equals sine x's range, right? And obviously because they're inverse functions, if we put them together, they cancel each other out, right? Leaving only x left, right? With their their domains here as well. But I don't think you need to know that too deeply. So you need to know how to derive inverse functions, trig functions, right? I know they're on your formula book as well. So, but to do that, we use implicit differentiation, which you guys learn later on. But at this point, you guys should have learned that now, right? So you should know how to do this. This is just some reading, so you can read through how we get to this derivative, right? Cool. So why don't we try derive arctan? Right. Let me pull up this specialist formula sheet. Um, so formula sheet. All right, cool. Where are your derivatives? There you go. So in your derivatives, the formula sheet says d dot dx of tan inverse x over a equals a squared plus x squared, right? So doesn't really look like that. Um, so how are we going to do this? So we can see that um, anyone want to have a go? Want to call out what might be the first step?
A is the same as, well, A is just going to be 1.
Yep, A is 1. Cool.
And then x squared, since it's squared in the derivative, you can just multiply that by well, you can square that, so it's x to the power of
Oh,
4.
so it's 4, right?
Yeah.
So it should be so therefore the derivative of this becomes um whoops.
1 over 1 plus x to the power of 4.
Yep. Yep. All right. So yeah, that was pretty simple. And then so you got to integrate. That's what we're more worried about, right? Integrating something in this form back into this, right? Um, so okay, how do we do this? So let's have a go at the first exercise. So, um, cool. Easiest way is if you have a look at your formula sheet. I know it's not the same sort of structure, but we'll get to that. So in your formula sheet, you got the integral. This would be, what function would we get this into? This would be a sine, right? Because it's positive, right? So we want to get this basically in the form of a square root a squared minus x squared, right? But we know that we can see that there's a coefficient in front. So how do we get rid of the coefficient? Well, we just factorize it out. Yeah. So uh, let's do that. So let's factorize this out. So definite integral. So we can factorize 25 out of everything. So we can say this is going to be 25, 36 minus x squared, square root everything, dot dx, right? And then so we can just factorize the 25 out. So square root of 25 is 5. So we can rewrite it like this. Yep. And then we can just take the 5 out because it's a constant, right? So, and we can do our integral. So using the formula sheet, we should be able to get that it's inverse sine. Well, a squared is equal to 36. So therefore a is equal to 6, right? So using that, we should be getting sine inverse x on 6, right? And our terminals are x equals 0, x equals 1. So we're just going to substitute that in, right? And it's just a definite integral. So we get 1 over 5 sine inverse 1 on 6 minus sine inverse 0 on 6. Okay. And we can see that the sine inverse of 0, just 0, right? So this is going to be a final answer. Yep. I think that was right. So, any questions?
Um, when you factorize the 25 out, it goes from 36 to 25 x squared.
Oh, I forgot oh crap. Yes, you're right. You're right. So my stupid ass didn't consider this, right? 36 over 25. Yes. So don't do me. Don't rush it. So a squared is actually going to be um 36 over 25. So a is going to be 6 on 5, right? And then you get 5 on 6 on here, right? 5 on 6. Oh,
Yes, I think
yes.
so.
Okay, cool. Then the answer becomes 5 on 6, right?
Yeah.
All right, cool. Don't make that mistake. All right. I think that's right. So let's move on. Okay, so this one we've got obviously an x squared plus 25. So without the square root, we can alarm bells are kind of going, okay, it should be 10, right? But it's not a constant at the t top. So why don't we just split the fraction apart, right? So we can split the integral into integral of 3x 9x plus 5 plus 5 over 9x plus 25. Oh, sorry, 25 dot dx, right? And now we have something workable. So what technique would we use to solve this? Anyone want to have a go? No? Yes? Maybe? Okay, so we would use a U sub to solve our the integral circled on the left here, right? And obviously we would use inverse tan to this other one. So, which one do we want to do first? Let's just do the U sub. So for our integral one, we get 3x over 9x squared plus 25 dot dx. So let u equals 9x squared plus 25. du is going to be 18x plus, oh, 18x, right? Cool, and then we just sub it in. So our substitution over u dot du over 18x, right? X's cancel out. It becomes 1 over 6, right? We put the constant at the front. Integrating it becomes u plus c. So it would be 1 over 6 ln 9x squared plus 25, right? Okay, second integral. So second part, we get 5 9x plus 5 dot dx. Okay, cool. So we can see that it's not exactly in the tan form as given in the formula sheet, but all we need to do again is just to factorize out, right? So I'm just going to keep the 5 at the front because it's a constant. And then we want to factorize what's on the denominator. So let's get rid of the 9, right? And that would be x squared on 25 like this. Yep. And then we can just, this would be 5 on 9. Let's just do the whole thing here. So we know that a squared is going to be 25 on 9. A is going to be 5 on 3. Right? So our integral becomes, so we get the constant. Let's write this out actually, so I'm not confusing anyone. Okay, so using a formula sheet, this is exactly, no, oh, well, not exactly in the form, but it's close, right? So we want to make it look like the form, right? Because the form we have on our formula sheet is this, right? So a squared is 25 on 9, a is 5 on 3. So we need to have a 5 on 3 here, so we can manipulate it to have a 5 on 3. So if we're going to have a 5 on 3 on top here, right? We want to make sure that we're dividing 5 on 3 in the constants region, right? So it cancels out and we haven't actually changed anything. So 5 on 3, so therefore we want to multiply by 3 on 5, right? Or dividing by 5 on 3. It's the same thing, right? Okay. So we can see that if we like literally just cancel out these two, we haven't changed anything, yeah? So now that we can do the integral, so our integral becomes 15 on 45, which is 1 on 3, right? And our integral becomes, oh, what's tan? Oh, tan inverse x on 5 on 3, which is 3x on 5, right? 3x on 5 plus c. Okay, so therefore, the answer to this question is going to be 1 on 6 ln 9x squared plus 25 plus 1 on 3 tan inverse 3x on 5 plus c. All right, does that all make sense? Yes, no, maybe. All right, that's cool.
Kind of
So
fell behind on the natural log part, but the rest of it makes sense.
okay, that's fine. Yeah, cool. So can you do this question without splitting it the fraction? So unless you can factorize it, right? Unless you can get a fact. Oh, I guess you can, right? Can you? Mm. What will be this? So no, you can't really, because you can't really divide and get rid of this, right? So the easiest way to is to factorize, to decompose it, I guess, like make it into two parts. Um, but unless you can like factorize this out, get rid of this entirely, or you, right? Um, but it's kind of hard to do it that other way, unless it's, yeah. All right, cool. All right, last of this. So we're told to evaluate this nasty looking integral, right? It's in a complete quadratic form, right? Not something that you've seen in your inverse trigs, but we can make it into an inverse trig form, right? By completing the square. So, let's complete the square. Let me pull up this. All right, so first of all, we want to get this out, right? So this polynomial. So why don't we just factorize our negative out because no one wants to deal with that. So it would be negative 3x minus 10. Yeah, cool. All right. Now, if we complete the square, we should be getting, um, negative x squared minus 3x um, plus 9 on 4. Oh, yes. Plus 9 on 4 minus 9 on 4 minus 10. Yes. Okay. So this is the same thing. Does everybody understand how I got the 9 on 4s? Just completing the square. Yep. Okay, cool. All right. And then we can factorize it, right, into, so which part is our square bit? It is going to be this bit, right? This is a perfect square, right? So this is going to be a square. So we can rewrite this as x minus 3 on 2 squared, right? And it's going to be 49 over 4, right? All right, cool. Now let's just rewrite our integral, right? So our integral becomes square root negative, oh, let's bring the negative 3 out. We don't want that there. And we'll use so it's all positive and nice. So 1 over, um, oh crap, this should be, oh, be careful of the negative. So this should be plus. Yep. All right. Cool. We've got this here. So it's going to be 49 over 4 minus x squared, x minus 3 on 2 squared, right? Dot dx. Um, okay. And so now let's do a u sub. So let u equals x minus 3 on 2. Du is just 1, right? So our integral becomes 49 on 4 minus x squared. Did I forget the square root? Yes, I completely forgot the square root in here. Square root. All right, cool. Minus x squared. Oh, sorry, u squared dot d. So now we're doing an integral in terms of u, right? So, okay, cool. First of all, a squared is 49 over 4. A is 7 on 2, right? So it doesn't really matter because you know how I got the constant out, right? Um, now it's going to be a arc sine. Oh, a sine inverse, right? If you keep the constant in and it's a negative, it's going to be a cos. They're both the same thing. So you can have an answer in cos and also an answer in sine. It doesn't really matter. Both solutions are correct. But we factorize the negative out, so we're going to have an answer in sine in the very end, right? So let's integrate. So using our formula sheet, which is here, and our formula sheet says integral of 1 over square root of a squared plus minus x squared dot dx is equal to sine inverse x on a plus c, right? So what we're just gonna do is just solve this in, right? So this becomes 2 on 7, right? So that's how you would do this one. Oh, actually, I've made a terrible mistake. U is actually 2, this should be U. And so we should be resubbing our U back, right? U is x minus 3 on 2 over 7. Let's see. There we go. That's our final answer. Cool. Does that make sense on how to do this question? I also apologize for my handwriting. It's kind of shit. So, um, but yeah. Cool. We're okay with inverse trig integrals. All right, let's move on then. Uh, uh, cool. Let's move on. So we have partial fractions, right? Um, so yeah, they're just polynomials written over each other, right? And you're just trying to factorize them. So we've got linear, distinct linear factors, right? So that's what we're gonna do. And so the first case is if m, so degree m here, so I guess what power it is in degree n. So if the top one is lower than the bottom one, so lower than the denominator, right? In this case, um, which is what we can see here because this is a cubic and this is a quadratic, right? So in this case, we just factorize our g of x, which is already factorized, and then do the partial fractions. Okay, so why don't we just do the partial fractions here? So how do we decompose this? Well, we've got 2x squared minus 5x minus 4. And then we've got x plus 1, x minus 2. And we want to write it in factors, right? So it should be a over x, b over x plus 1, and c over x plus 2, right? And so if they haven't already given us in a factorized form, you've got to factorize it beforehand. Yeah? That makes sense? All right, so we're going to multiply by the denominator by everything, okay? So we're just gonna do 2x squared uh, minus 5x minus 4 uh x plus 1 x minus 2 b x x minus 2 plus c, I'm gonna move this all the way across, plus c, uh oh shit, that should be a minus, my bad, c x plus 1. Yeah? So what we've just done is multiply through by denominator. Yeah? Okay. So now that we've done this, we can, I guess, expand. Right? There is a way where you can just sub in the roots of each factor and you can cancel it out and it's nice, right? But that only works for some partial fractions. So I'm not going to do the shortcut here. I'm just going to multiply through and equate coefficients because I think that's, I guess, the best way. Like it's a guaranteed way, right? So we're going to just multiply through, right? So this is a quadratic and it becomes x squared. Um, crap, can't do this, can I? Minus x plus minus 2, right? Plus b x squared minus 3x. Oh, sorry, 2x. I can't even read my own handwriting. Plus c x squared plus 1. Yeah. So now that we've got this, we're going to equate coefficients, right? So equate coefficients. So for the x squared term, right, we've got 2 on the left-hand side. We've got a on the right-hand side, and then we're going to plus b plus c, right? For the x term, we've got -5 on the left-hand side, and on the right-hand side, we've got -a, right? Um, plus minus 2b, right? And that's it. And for the one term, so x to the power 0, right? We get -4 on the left-hand side, right? -2a, no b term, and then plus c. So you've got system of linear equations, right? So you can solve this by back substitution, or you can do it in simultaneous equations or Gauss. Either one works, right? I wouldn't do Gauss. It's shouldn't be that hard. So what can we do? Well, both of the A's, there's A's in both of these, so we can do a back substitution. So, yeah, why don't we do that? So basically, equation 1, equation 2, equation 3. Okay. So, A. I'm gonna have to substitute it anyway. So let's just let B be the subject and see. So for 2, we're gonna say B equals -5 plus A over -2, right? 3 is gonna be rewritten as C equals -4 plus 2A. Yeah. And then we're gonna say sub in 2 and 3 into 1. So we're gonna get 2 equals A plus minus 5 plus A over -2 minus 4 plus 2A. You solve for A, and your solution should come out to, I'm not going to be bothered to solve this because it's just algebra. A equals 2, B equals 1, and C equals -1. Okay? So that's what you should get, and you should be rewriting this partial fraction in partial fractions, right? So A over 2 plus, oh, sorry, 2 over x plus b 1 over x plus 1 plus negative minus 1 over x minus 2. So, sorry, let's put that down. X minus 2. Okay, cool. Does that make sense? And then you can just integrate this. So yeah. All right, cool. So if we have something that's repeated, right? So a perfect square, we're gonna rewrite it twice. Yeah. That's just the way it is. You just gotta remember that. And then if we have something non-linear, like if we have an x squared inside, we're gonna write the numerator as bx plus c. Okay. Here's a table. It's a really useful table. I don't think as specialists you'll ever get this, so just, focus on these. Yeah. Uh, so let's try our first integral. So for the cases where the numerator is equal or bigger than the denominator, we have to use long division, right? It makes life really easy to integrate. So why don't we try long division for this? Okay. And so if we see this, so long division, right? X squared plus x plus 4, x squared minus 2x minus 3, 1. x squared minus 2x minus 3. Remember, this is minus here, right? So we're going to get 3x plus 7. So there's a remainder of 3x plus 7. So we're going to rewrite this integral as integral of 1 plus 3x plus 7 divided by our denominator, right? Because we've just done long division. We're rewriting it, yeah? Dot dx. Okay. So we can factorize our denominator, right? So let's just ignore this one for a second because we know how to integrate that, right? But so let's focus more on the rational function. And so this becomes 3x minus 7 plus 7 divide by, and we can write it in terms of two factors, and it's going to be negative 3x plus 1. Yeah? Cool. All right. And then we can write it as in, a over x minus 3 plus b over x plus 1. Cool. And we're just going to multiply through. So it's going to be 3x plus 7 equals a x minus 3. Oh, sorry, x plus 1 plus b x minus 3. Right. Um, And then so you get two equations. You get a plus b equals 3, and then a minus 3b equals 7. So doing simultaneous equation, you should get a equals 4 and b equals negative 1, right? And then we just, therefore our integral becomes 1 plus 4 over x minus 3 plus minus 1 over x plus 1 dot dx. Okay. And then we can just integrate this. So x equals L 4 ln x minus 3 minus ln x plus 1. Let's see. Yep. All right. Does that make sense? Pretty chill. All right, cool. Let's move on. So we're gonna do this one, right? So we can see that there's a non-linear factor. So we're gonna have to make the numerator, be ax plus b, something like that, right? So, okay, let's have a go. So we're gonna just say that, let's do our partial fractions first. So for x over equals, right? It's going to be ax plus b over x squared plus 4 plus c over x minus 2. Yeah? All right, cool. So we're going to expand this. Oh, first we're going to multiply through. So 4x equals ax plus b, x squared plus 4 plus c. Oh, whoops, wrong way. Plus c, x squared plus 4. Okay. And then we're just going to equate, right? Equate coefficients. Do I want to expand it? Yeah, let's expand it. So this becomes ax squared plus bx minus 2ax minus 2b plus yeah plus cx squared plus 4. So if we get all the x squareds terms together, we get a plus c. If we get the x's together, we get b minus 2a, and if we get the 1 terms together, we get negative 2b plus 4. Okay, so we're going to equate coefficients. So for the x squared, so equate coefficients. So on the left-hand side, right, we have x squared, so it's going to be 0, right? That's going to be a plus c. For the x terms, we get 4 equals b minus 2a, and then for the ones terms, we get 0 equals negative 2, that should be a c, to negative 2b plus 4c, okay? Um, Simultaneous equations, right? We can say that c equals negative a, right? And then if we substitute it in, do some algebra. I'm not going to do it because I think you guys can do that by yourself. But if you guys don't know, please let me know and I'll go through it, right? C equals 1. Okay, so that should be your your coefficients, and we can just rewrite our integral as is. So it should be negative x plus 2, x squared plus 4, plus 1 over x minus 2. All right. All right, cool. So what do we do with this one? How do we solve this integral? Any suggestions? No? Yes? Maybe? Anyone want to talk?
U substitution.
You sub? Okay. Close. But okay, yes, we're gonna do a U sub, but what do we do first? What do we want to do first? Because we can't really factorize this this x plus 2 out, right? But we can split it. So let's just split it. Okay. Right? We're just rewriting it in a more simplified, I guess, in a longer way, but it's still the same thing, right? So this we're going to use U sub. This, what are we going to use? Anyone want to have a go? No? Yes? Maybe? Okay, so we're going to use tan, right? This kind of looks like tan. This we know how to do, right? So we're going to use U sub for this. Um, this we're going to use inverse tan. And this we know how to, the last one we know how to do. All right. I'm just gonna skip through it. So, actually, no, let's not be lazy. So we're gonna for the first one, let u equals x squared plus 4. du is 2x. So our integral becomes negative u, um, sorry, negative x over u, whoops, over u dot du over 2x. All right, you can see the x's cancel out. Plus, um, this is already in the form, so I'm just going to do the integral already. So du plus, this is going to be tan inverse x on 2, right? Plus ln x minus 2 plus c, right? And so all we need to do is this last bit. So this is going to be, oh, can I shuffle things up? No, that's all right. This is going to be ln u 1 over 2. So it's going to be 1 over 2 ln x plus 4 plus tan inverse x over 2 plus ln x minus 2 plus c. Yeah? So that is our final answer for that. All right. All right, cool. We're good on time. So let's move on to by parts, which is the last technique you learn, right? Or already have learned. This is the I guess how they've got up to it, right? We know this as, I guess, UV minus VDU, right? VDU, yeah. Because all of these x's, the x's just cancel out. You get the same thing, right? Um, so let's try it with the first one. So how do we recognize by parts stuff and not confuse it with, things that we might use for um U sub, right? U sub is like if we see that the derivative is like, um the derivative is um we can decompose, right? We can get rid of. But for this one, it's like we can't really. If that kind of makes sense, like you sub it back in and you can cancel it out. But this one, it's like if you sub it back in, you won't be able to cancel out. So that's when we use by parts. Um, all right, so for the first one, we can see that this is a classic like example of when to use by parts, right? Because you've got a product between two functions, but if we let u with one of them, we're not going to be able to cancel the other one out, right? So that's when we use by parts. So what is the thing that we can get rid of? Well, we know that if we derive x, we're going to get rid of x, right? If we derive something to the e, we need to- so why don't we just do that? So we're going to let uh, rule for by parts is udv minus vdu, right? And so if we let u equals x, du is 1, v dv equals e to the 5x, and v equals 1 over 5 e to the 5x, yeah? And so we can rewrite it now. So it's going to be uv, so x on 5 e to the 5x minus 1, which is just 1, times e to the 5x dot dx, right? Oh, shit. 1 on 5. Right? And we can just integrate what's on the right here pretty easily. So it's going to be x on 5. It's going to be minus 1 on 25 e to the 5x plus c. Yeah, that's pretty nice. Okay, next one, same thing, sort of thing, right? We've got x squared and we've got a ln log, natural log, right? But we can see that if we derive ln x, we kind of get rid of it because it becomes 1 over x. So let's just do that. So I'm gonna quickly just do let u equals ln x. Whatever you let u equal, that's the one that you're deriving, yeah? So that's the one that you want to get rid of. Um, du is equal to ln, what else? Shit, 1 over x. Idiot. Um, yeah, cool. Uh, and then we're gonna say dv is equal to x squared, so v is equal to x to the power of 3 over 3. Okay. We know that our formula is this. We're gonna substitute that in, right? So uv is gonna be x on 3 ln x minus v, which is going to be x on 3 times by du, which is going to be 1 on x, yeah, dot dx. Just substituting it in. And then solve, right? So integral of x squared over 3 is going to be x on 3 divided by over 9. Let's see. Oh, and we've got to make sure to put but because this is a definite integral, we've got to make sure to put our terminals in, right? Completely forgot about that. X equals 1, x equals 2. And we're just going to sub it in. So we're going to sub it in. Crap. 8 on 3 ln 2 minus 8 on 9 minus 1 on 3. Oh, ln of 1 is 0. So our first term is going to go to 0. And this is going to be 1 on 9. Yeah? Cool. Now let's try and simplify this. We got 8 on 3, ln 2. Plus 1 on 9. So this is going to be minus 7 on 9. Yep, that's our answer. All right, cool. Any questions? No questions? All right, let's continue. All right, so we've got a very classic example, right? What happens if it's just one function? You know, why are we using by parts when it's just a single function? Well, we saw that before. We want to derive ln x, right? Because we don't really know the integral of ln x, right? So we wouldn't do the other way, okay? But what we can rewrite this function as 1, right? 1 times ln x. And you basically got two functions, right? So we let u equals log x, du is equal to 1 over x. dv is 1, v is going to be x, right? So put it in a formula. uv is going to be x ln x minus integral of v du times 1 over x, yeah? And so we're just going to get x ln x minus x plus c, yeah? Because these two cancel. The x's cancel out. You're integrating over 1. Integral over 1 is just x. And we can also use this trick, right? Putting just 1 at the start with inverse trig functions, right? I think last year when I ran a specialist math, I went through a few of these integrals and you guys happened to get an inverse trig function. So if they asked you something like, oh, integral sine inverse x, right? Just use the same trick. So we'll let u be sine inverse x because you can derive that. And then we let dv equals 1, right? And we did the same thing. All right, cool. Let's just do this last question and we can call it a day because we've gone through pretty all of this techniques and stuff. And then we'll go applications tomorrow, right? So last one is e exponential and sine. And what's the issue with exponentials and sine is that they're circular, right? You can't really get rid of them. So how do we do this? You're about to see, you've got to do it twice, right? You've got to integrate into by parts twice. So let's do it the first time. So let u equal e to the 3x. du is going to be, oh, it doesn't really matter. Actually, in this case, it doesn't really matter which one you set as e and which one's u, right? So LV. So let's just set E as the one. So du is going to be 3x dot dx, right? dv is going to be sine 2x. So v is going to be 1 over 2 half negative half cos 2x, yeah? So we're going to put it in our formula, right? So u is 3 e to the 3x. V is negative a half cos 2x minus v du. So v du is negative a half cos 2x. And du is times by 3e3x dot dx. Okay, cool. Now we're just gonna consider this one here, right? First of all, let's just get rid of the constants because getting rid of constants outside is nice. So we're gonna put this as e negative a half, the negative half at the front, e3x cos 2x. This is going to be plus a half, or 3 on 2 actually, 3 on 2. Cos, oh, let's put the e at the front, okay? Dot dx. Okay, cool. Now let's only consider this one. So I'm going to do this in red. So let u equal e to the 3x. du is 3e 3x. Oh yeah, and be consistent with the whichever one you select first as you're deriving and the term that you're going to be integrating, right? Because or else you're just going to go in circles and not actually get to. You'll get the point at the end. So dv is cos 2x. So we're going to integrate this and it's going to be a half sine 2x. Yeah. So in our formula, yeah, we're going to get u, which is e to the 3x, v, which is a half sine 2x, minus v du, v, which is a half sine 2x, and u is just e to the 3x, right? And you can kind of see that we've gotten back, this term has gotten back to our original, right? So if we were to write the entire thing, right, e to the 3x, so we're going to take the left-hand side, so e to the 3x sine 2x. That's our original integral. And then our right-hand side is the process that we've done. So we're going to take negative a half e to the 3x cos 2x. And then we're going to take this bit here. Yeah. So this is going to be plus 3 on 2. And in this brackets, we know that the red here is going to be what's in our brackets. Yeah. So this is going to be a half e to the 3x sine 2x. Oh, yeah. This is supposed to be sine. Yeah, no, it is. No, I'm just. Oh, because this is supposed to be cos. Made a mistake. Cos. Okay. So it's supposed to be cos. No, that's supposed to be sine. I'm just tweaking. No, I'm idiot. Anyways, half sine 2x. I'm just going to keep it here. So integral of a half sine 2x e to the 3x. Yeah? Closing the square bracket here. So what can we see? Well, we can see that we can use some basic algebra and just add this on, right? This integral, we're just adding integrals. But obviously this is within the square brackets, so let's just expand, right? So we're going to expand our right hand side. Yeah. Plus 3 on 2. So this is going to be 3 on 4, e to the 3x sine 2x minus 3 on 4 sine 2x e to the 3x. Okay, cool. So now we've got our expanded version. We can, oh, I forgot the integral sign. So, yeah. We can see that we can just add this integral onto our left-hand side, right? So we're just going to say that therefore this integral becomes 1 plus 3 on 4, which is 7 on 4, integral e to the 3x sine 2x, should be a 3, dot dx equals, which is going to be equaling to this, right? Okay. And then so therefore, if we wanted to, you know, get it back to what the question originally asked, which is just, this integral, we just divide by the coefficient here. So therefore, our answer becomes negative a half e to the 3x. I'm just going to put the 7, 4 and 7 at the front here because I cannot be bothered to expand. Okay, and then plus c. Does that make sense? It's just 2 and 2 integration by parts. All right, that's our answer. All right, cool. I'm gonna stop it here. So thanks for joining for today. I know that was a lot. We went through quite a lot of questions within the hour, well, hour 20. So yeah, we'll go through some of the applications tomorrow. So obviously area under the curves, volumes of revolutions. And then I think we're gonna stop on there's some parametric stuff in there as well. So Simpsons and then also PDFs, right? Exponential PDFs. Okay. Um, yeah, so for tomorrow, would you guys rather morning or afternoon? Or what time would you guys like? That is if you're coming. So, you know, does anyone want to speak up or like afternoon? You can type in the chat. So, afternoon? Do you like this time afternoon or would you like later? Or would you like earlier? Like 2 or 1, something like that. And this time or later. Okay, yeah. All right, so we can do this time is good. So 4 o'clock. Okay, cool. So okay, I'll do 4 o'clock tomorrow. So yeah, I want to say like if we get like 20 people, I'll run it. I'll completely run it. But if we don't, I'm gonna cancel it. So I guess yeah, it's depending on how many people join. Yeah. But I'll definitely, yeah, if definitely 20 people show up, I'll run it. So we'll continue with the slides. And we should be able to finish the rest of this. And depending how I feel, actually, yeah, tomorrow we'll spend finishing the rest of this, and then we'll move on to related rates and some differential equations. Yeah. Okay. All right. Thank you so much. I'm going to stop the recording now. How do I stop this? All right, cool.